without further ado, we'll get into our second module here, which is the basics of system sizing, right? What should we expect to see in a solar system, especially if we're designing with a contractor, if we're doing a first design in-house, and a very first pass exercise of how we would size our systems. So, looking at these two drawings of solar systems, one an illustration from the 90s, right, from the dawn perhaps of solar water pumping as a more or less financially acceptable option, and the other a very new illustration from the Water Mission UNICEF resource. So as we look at these, right, we can see that really over time, this basic way of illustrating solar water systems hasn't changed all that much, right? We're going to need our solar array, our rack, and our panels themselves, right? The structure that they're mounted on. We're going to need a controller, right? Something that will condition the electricity coming out of the panels for something that will be used by our pump. We're going to be needing our well and, of course, our pump. In these cases, we're looking at submersible pumps. There are solar options for standard centrifugal pumps, but you can also connect an inverter and use a standard AC pump. In addition here, something that we've gotten in these last 30 years is a treatment enclosure. Here, at least chlorination. We might also consider other treatment options, and we really like to get into that a little more detail. An elevated tank, fantastic to have a hillside, but in many cases we can't do a hillside and we need to do water towers. Some sort of water meter, another addition that we've had in 30 years, is actually metering what's coming out of our tank. And finally, our distribution system. So what's missing from these images? Give you all a couple of seconds if anyone has any feedback. What's missing out of these drawings that we'd expect to see in the real world? Very well. So for one, what we discussed earlier, a little bit of security for our system, right? Might make for a less attractive image, but a more realistic one, right? Some fencing around those panels, somewhere where it wasn't abandoned in the middle of the field, but was actually in a location where people could watch them. We'd want to see some sort of lightning protection, ideally, for those panels, right? Something to prevent damage during storms. We might need some additional treatment option beyond just chlorination. For example, if our well has naturally occurring iron, we may want to do some sort of treatment for that inline. Hardness as well, things that can really generate rejection of these water sources by the user population. And finally, we'd love to see distribution that wasn't tap stands, right? We'd love to see connections that had water in each house and a water meter, right? Really thinking about what that next level of service would look like for communities. Those very, very basically what systems we'd expect to see in a basic solar design. So quickly, some notes about what solar water pumping components are different from their sort of AC or their genset equivalents. First off, sort of the way we think about pumping in solar systems is slightly different from what it would be with other power sources. Solar water pumping is obviously limited by the number of sunlight hours that we have in the day, right? In equatorial conditions, we can get 9 to 11 hours of pumping depending on the size or the oversizing of our solar array. So in many cases, we'll see a grid like this, right? We'll see a chart of the number of watts per meter squared, watts per surface area that we have of sunlight in an area. And we integrate that into peak sun hours, PSH, which is the equivalent of 1,000 watts per meter squared. So in a lot of cases, when we see that data, right, we'll see an equivalent that we saw in the first step, we'll see an equivalent in peak solar hours to what we saw there in overall solar hours, right? So don't be surprised if you're looking in literature, particularly older literature, and rather than seeing watts or kilowatts per meter squared, you see peak sun hours, one and the same. So since we're pumping during this much more limited part of the day and not pumping between sunset and sunrise, we may need a comparably larger pump and we may need a higher yielding source in order to get sufficient water during that briefer pumping period. With the genset, with the AC grid, we could be pumping 12, 14, 16 hours a day. I've heard of cases where people were really pumping all 24 hours. Not a best practice, but certainly something you can do with other energy systems that's not feasible with solar. Now, this is the sunlight in an ideal day, right? Peaks at solar noon, comes slowly down until sunset towards sunrise. A real day is very rarely like that. A little bit of cloud cover will vary this a lot. And so we'll need power conditioning or a variable speed drive if we're using a non-solar direct pump. If we're using a standard centrifugal multi-stage pump, we'll need that variable speed drive to make sure our motor gets up to speed, right? And is actually moving water within our pump, right? Otherwise, the stages may be spinning, but they actually won't generate enough force to move water through our system. So this means that we really need to be very attentive about the quality of our power conditioning, or better yet, use direct solar pumps, especially for small systems that are helicoidal, positive displacement, or other systems that really pump even under less than ideal power conditions. Now, knowing that we have variable power conditions, when we use design tools from those high quality manufacturers, right, from Goodfellow, from Franklin, from others that may have similar tools, they'll generally give us a chart of water output during the month selected, right, during our worst month for design. So we don't have to eyeball this. Most of the time, we can actually get a very accurate estimation of what our water output will be throughout the day when we use a manufacturer's website. So always need to double check those numbers, but something that we should expect to see when we get a quote on equipment from an outside contractor, when we get a quote on equipment from an equipment provider, is really knowing how much water can we expect from this system under our worst month conditions. Another change when we think about solar water pumping versus other pumping systems is that because we do have a little bit more uncertainty, right? The solar water system can be functioning perfectly, but let's imagine we had a few days that were cloudier than average. In those cases, we're going to need a larger reservoir to really make sure that we're able to sort of carry through those bad conditions and ensure proper operation of the system. So the rule of thumb in many cases is that we want a full day's water consumption in our reservoirs. And in cases where we need to build water towers, that can be a significant expense, right? Additional reservoirs, especially if we're working in, really regardless of material, but particularly if we're working in polyethylene, if we're working in geomembrane, may not be that much of an expense if we can use a hillside location. But where we need to build water towers, this can be very, very pricey. The photo here is a community here in Ecuador that about 20 years ago started in on building a water system and actually ran through their entire budget just trying to build the water tower. So half built for 20 years. We completed it about 3 months ago here with a local partner, and it's been functioning nicely, but goes to show you that a water tower really can suck up resources versus the other elements in our systems. So if you do need to use water towers and they become prohibitively expensive, one option with solar may be to do the heaviest part of the lifting with our solar system and locate additional reservoir space or water treatment steps, especially if we need to do something that's space intensive like sand filters at ground level, right? Much cheaper to build a little concrete pad here on the grade, do our treatment at ground level, and then have a much smaller solar pump or a much smaller AC pump or genset pump that just completes these last 8 or 10 meters of lift to the water tower, rather than trying to lift everything and have our entire treatment occurring in this elevated location. So really, when we start to integrate solar and we need water towers, we need to be creative about how we're creating the most cost-effective solution for communities and the one that's easiest to maintain. So those are our different considerations for solar pumping compared to other pumping options. Now, what should we avoid? What sort of shouldn't pass the laugh test if you get a a proposal from a design firm, or if you get a proposal from an equipment provider, and you see these items, right, with all due respect, these people may not know what they're talking about. So what do we really want to avoid? One, tracking arrays. Formerly, when solar panels were much more expensive, a tracking array, one that really moved the solar panels as the sun moved through the sky, might have been a reasonable option. But now the solar panels are so much cheaper than they were in the past that it no longer makes sense to have a complex mechanical system that you're going to need to be maintaining, right? You're much better off installing more panels, which is an electrochemical system, very simple, really needs very little maintenance, and a much cheaper option. Install a fixed array and install a few more panels. You'll thank yourself in the future. Another thing to avoid are batteries, right? Very common to see this nowadays in designs. Battery technology has certainly come a long way, but for the moment, batteries are still a large expense, still a very complicated element, still something that's very failure prone, depending on, especially on storage conditions, on how well the wiring is done, and something that is almost never justified. In general, we want to let extra elevated water be our battery, be our storage of energy, right? If you can build a larger reservoir, there's your stored energy. You don't need to be trying to store electricity. And the one case where you could perhaps see batteries being justified is if no other backup system was feasible. You couldn't get fuel, diesel, gasoline to the region. You had no grid possibilities. And if you had a very low yield source, that meant you needed to be pumping more than those 9 to 11 hours a day. But with all of those conditions in place, batteries may still not be the right choice. It may be more cost effective to develop an additional higher yield source rather than investing in batteries and their upkeep and eventual replacement. Other things to avoid, of course, costly accessories. If your fencing or if your lightning protection for your panels costs more than the panels themselves, you should probably reconsider what your protection looks like, right? Some welded bolts may be a much more efficient solution to how to protect your panels from theft than a fencing setup that costs $5,000, costs $8,000. It seems like common sense, but you do see it in proposals every once in a while. And then finally, something to avoid are inverters for small systems, right? Going back to the previous slides, right? That variable speed drive, that power conditioning for a centrifugal pump can be very complex, can be very hard to get right. And so in general, we want to use direct solar pumps, direct DC pumps, whenever it's feasible. If there's no tech support for those in country, okay, then an inverter and an AC pump may be your best choice. If you can't get an AC pump that matches your water conditions, if you really need something that handles high turbidity loads, that may be another condition where you should be using a standard AC pump and inverter. But in general, you want to avoid those for their complexity and for their loss of efficiency in the system. Next, we want to consider how we're building for the future. Many things may be easy enough to do in a modular fashion. We're very, very big fans of using these 2,500 liter polyethylene tanks here in Ecuador because they're lightweight, they're easy to move, and it's easy to add additional capacity as needed as the population grows. So when you have system components that are easy to roll out in a modular fashion, things like reservoirs at grade, things like treatment, things like more PV panels, if you want to do a larger pump in the future, leave space for those in your initial layout. Nothing more frustrating than having to renegotiate land access when you need to put a little more reservoir, a little more treatment capacity in. However, we don't need to over-design things, going a little bit towards Katya's question about how system design should be done for how many years, right? Basically, the components that are going to be a real headache to change out, things like pipelines, things where we need to be trenching, things where we need to be negotiating land access, those we should really design for their maximum useful lifespan, right? Design those for 20 years out, design those for 25 years out. Going up a size in pipe is generally a minimal expense compared to the cost of trenching, compared to the difficulty you may have in reorganizing the community to replace that pipe in the future, right? And really thinking about what's our maximum access going to look like, right? Perhaps in the future, we'll go from single tap stands to multiple tap stands. Perhaps we'll go from multiple tap stands to household access. So really think about what your max flow rate may be, because the expense there is going to be minimal compared to the effort put in to install those components. But there are other things that you really don't need to design for 20 years out. Your pump won't last for 20 years. And so your initial pump doesn't necessarily need to deliver the water your system will need after 20 years of population growth, right? You can add additional solar panel capacity. You can install a larger pump, assuming your source will meet that demand. But you don't need to install a 3 kilowatt pump if today's consumption really only merits a 1.5 kilowatt pump. So there's a balance between what needs to be designed for the future and what only needs to be designed for a couple of years in the future. So a quick plug for some green empowerment tools that we'd be very happy to share. Many national norms are really designed for larger systems, systems with 500 connections or more, or 500 access points or more. And so the ways that flow rates are calculated through pipes often don't really apply or are not sufficiently demanding for small systems, right? Imagine if you have a pipeline with 500 connections, the chance that all 500 will be open at any one point in time is very low. But if you have a pipeline with 2 connections, there's a very high chance that both will be open simultaneously. So we really do like to recommend this design factor called simultaneity. And we've designed a handy little Excel tool that will allow you to design pipelines using that simultaneity factor and designing them also according to what time of day your consumption is occurring during. So we're happy to do those tools and also do a quick walkthrough on how they're used if there's interest from participants in learning how to use them. But enough of that plug. Let's get back to our example in Bianca.
Yes,
right?
so maybe just to cut you short a bit, there's a question in the chat
Sure.
from Moses on theft. So he's asking, how does the bolt system protect from theft, since the thieves can undo the bolts at night when no one is there? So we just wanted to put that out before we continue.
Of course. So really, as well as being bolted in, we want to look for non-standard bolts, right? Don't use just a standard hex bolt. Look for something that's called a coconut-headed bolt here, or a smooth-headed bolt. That's really requires special tools to undo. Or what we've seen be very functional in Nicaragua is to use standard bolts and then to weld a small strap of steel over those bolts, right? We'll get into security a little bit more coming up, but that's a great question about what can we do, if not to prevent, but at least to dissuade theft. So we will definitely get into that a little more depth, and I'd really like to hear as well any other experiences that folks have had in sort of theft-proofing systems when we get to that in Module 4.
Okay.
Thanks so much. So going into back to our example, right? We have a system there in Bianca. So what size of solar system would we need to meet demand? What are we going to need? Going back to Module 1, we're going to need our estimated water consumption. So let's assume that we're moving up in the world of service levels. And rather than meeting sphere standards, now we're meeting standards that are more common when we see household access. So let's assume that we're using 50 liters per person per day of water consumption, right? We want to put in a population growth factor. Let's assume there's not sort of explosive growth, but standard geometric, 3% growth a year. And we need to assume a little bit of wastewater for leaks. So that's generally for a well-built system. For a new system, we can keep that as low as 5%. So we have 520 people in the community. A simple multiplication, 49 cubic meters a day of water. Our total dynamic head, right? The sum of all the resistance, the gravity and the friction that the pump will need to overcome to deliver water to our tank. We can calculate the friction losses exactly, or we can just assume them at 5 to 10% of our static head. So let's assume that here in Bianca, We have our dynamic water level in the well, 30 meters below grade. We have our tank located on top of a 50-meter high hill, and our tank is 4 meters tall. So we need to deliver it at the top to the inflow. So our total height is 84 meters. We're going to multiply that by an approximate friction loss of 7.5%, 90 meters of height. And then we have this magic number, right? This magic number is what allows us to turn our worst month solar design. So if we go back to June, right? If we go back to module 1, we remember that our worst month was June, 3.36 kilowatt hours. Remember, 3.36 peak solar hours. We want to use older terminology. And this magic number, 170.6, accounts for all of our losses, all of our conversions within the calculus. And so with these 3 data points, our worst month, our estimated water consumption, our fantastic. Are we back?
Yes, we can see it. Thank you.
Great. So using these 3 data points and our magic number, we can do a back of a napkin calculation, right? A very simple illustration here of Bianga's system, our well, our hill, our tank, calculate our total dynamic head, look online to get our peak solar hours or our yield, our solar radiation in the worst month, and our consumption. We just multiply consumption multiplied by total dynamic head divided by our magic number multiplied by the worst month peak solar hours. This gives us our array size, right? So using this for the Bianga setup, we want to be delivering 49 cubic meters of water a day at 90 meters of head. In this site, we're going to need 7.76 kilowatts of panel. We can round that up to 8. So manufacturers' online design tools, right? If we're discussing those high quality manufacturers again, may use other estimates. Obviously, their calculations for the pump's yield are going to be a little more accurate, but we should see them align more or less closely with this back of the napkin calculation. Now, what is this going to cost? If we're doing really a one-off system, costs can range for $3 to $4 per watt of array. And that's for the whole system installed, right? So that's the array, its rack, the pump, any sort of pump controller you may need, and the costs for installation, of course, profit for the installer. If we're doing multiple systems, or if it's an area of easy access, those prices may be significantly lower. But this gives us an ability to ballpark that for our Bianga setup, we should be looking at $24,000 to $32,000 to install this solar system. Obviously, you'll need a more exacting design, but this really allows you to see that this isn't rocket science, right? This is not beyond the reach of anyone who's already doing water system design and implementation to really get ideas of how large of a solar system you'll need. And this allows you to really decide, is solar something I can consider, or is solar going to be cost prohibitive because either A, donor support is going to be difficult to get, B, this site may be abandoned within a couple of years and this investment isn't worth it, or C, I have other sunk costs. And so that's where we're going to get into now.